Yep, it's a good start. Good start. Okay, there we go. Good start. All right, so yeah, first things first. What are we doing? So I guess basic comparison. I guess that should be the first thing. So theorem and the basic comparison test. Okay, so that means now we have two, and if you want, you call them basic comparison tests for integrals or basic comparison tests for series. It's probably contextually obvious which one you're talking about, right? Like if you're talking about series, you're talking about this one. If you're talking about integrals, you're talking about that one. Suppose AN and BN are sequences. Such that 0 is less than or equal to AN is less than or equal to BN. And, oh no, I guess we can stop there. So 1, if BN converges, and again, I'm doing that lazy thing where I don't necessarily include all of the indices because we implicitly we know we're taking an infinite series. Then AN converges. Okay, and number 2 doesn't need to be explicitly stated because it is just the contrapositive of this statement, but we'll include it anyway here. If AN diverges, then BN diverges. Right? So pretty much the exact same statement for improper integrals. For improper integrals, we had said let f and g be non-negative functions. And then if the improper integral of the bigger function converged, it forced the smaller function to converge as well. And then again, the contrapositive of that statement is if the smaller function diverges, it forces the bigger one to as well. And again, it's some sort of like squeeze theorem in a sense, right? You've got the dominating function eventually sort of levels out and converges to a finite number. That has to be true of the smaller function as well, right? Almost just not quite a monotone convergence theorem sort of thing, but well, I guess it is a monotone convergence theorem thing, right? That's basically what we use to prove it. So yeah, a monotone convergence theorem thing. Okay, and the proof is the proof is identical. Where again, you just kind of appropriately change things depending on, wherever you see an improper integral, you now put a sum and so on and so forth. So, okay, what do I want to say here? So let's say let AN and BN be the partial sums of AN and BN, right? Okay. So what do we want? So both are increasing sequences. Not that it matters, or both of the partial sums are increasing sequence. Both, or I guess we should say non-decreasing because I only said they had to be greater than or equal to 0, right? So both AN and BN are non-decreasing, right? Since their terms are positive. So every time, if you're adding a non-negative thing to your sum, well, the next partial sum has to be bigger than or equal to the previous one, right? So we've talked about that before, which is why I'm not repeating that part of the proof. So both of these are non-decreasing. Okay, so now if we assume that, well, let me call this BK now, converges. What does that mean? That means BN converges, right? And moreover, we're going to have AN is less than or equal to BN is less than or equal to the sum. Let me put the indices in for this one. See, this time I think the indices are important because BN is the partial sum, and I really want to make it clear on the right-hand side, that's not the partial sum, that is the full sum. So, right, obviously any of its partial sums is going to be less than its limit, just because the thing is increasing. So now we've bounded an from above. So by the monotone convergence, we're a non-decreasing sequence. We're bounded from above, we must converge. All right, so thus, by the MCT, an converges, right? And then the opposite direction is just the contrapositive of this statement. If you don't converge, that means you diverge. All right. Now, the examples are generally sort of the same as what you would do, but maybe we can do something really quick here. All right, so let's say, what do we want to do? Sure. So determine k equals 1 to infinity. I guess we could start at 0, whatever. 2k plus k converges, right? So, okay, what do we do? Again, as we go off to infinity, the thing we have to ask ourselves is sort of what is the dominant behavior, right? Like what is the thing that's really, affecting the behavior of this series? And if we look at the denominator, we've got this 2 to the power of k, we've got an exponential, and we've got this k term. Well, the k is probably not contributing much, right? By the time k is equal to 10, the exponential portion is 1,000, and k is just 10, right? So it's not really doing much. And by the time k is equal to 20, that's gotten worse. So as k goes off to infinity, it seems like the 2 to the k term is dominating, right? So let's see if we can set it up so that we can compare this series to 2 to the k. And of course, it is set up so that we very nicely can. So note that 1 over 2 to the k plus k. In this case, because I started at 1, it is actually strictly less than 1 over 2 to the k, right? And then that thing converges because it's a geometric series whose common ratio is less than 1. Converges because it is a geometric series. So by the BCT, so too does the left-hand side, right? So by the BCT, converges, great. Right, that's a pretty easy thing. It's not too bad. Again, though, just like with our improper integral, if I'd made this like minus k, right? So if this was 2 to the power of k minus k, immediately our life becomes so much harder, right? Because the problem is that the natural thing to do if I had 2 to the power of k minus k would be to switch that less than sign to a greater than sign. And that's useless, right? If I know that I'm bigger than a convergent series, that doesn't tell me anything. Same thing is if I'm less than a divergent series, that doesn't tell me anything either. So you have to make sure, right? You have to be careful about your inequalities and make sure everything works out. And sometimes it won't. So we're going to have a limit comparison test later down the line, in order to help us do that. Do we want another? Maybe let me do the. Yeah, you know what? Let me do another example quick because these are pretty quick examples, so we can just do a quick one. Let's do a divergent one, right? So the sum. All right, what did I do here? I guess I need to be careful about my indices when I do this one. 3 to infinity. Okay, something like this. again, you can imagine like if you had to do this without, so first of all, if you had to find the exact value of this, who knows? And then trying to figure this thing out in terms of its partial sums is probably a little bit tricky, right? This thing definitely, is heading off to zero. So what are we going to do? Is this what I want? Yeah, I think this will work. Okay, so again, let's note, basically what I want to say is this thing kind of looks like 1 over root k, right? Like if I didn't have that stupid -2 term, I would be able to say this is 1 over root k. And we don't have a p-test, so we don't necessarily have a way right now, at least, of saying, okay, 1 over root k should diverge, but that's fine because I can compare 1 over root k to 1 over k, right? So note that this is going to be greater than root k over k, which is equal to 1 over the square root of k, like that, right? And then sort of the crux of the next bit is that this is actually bigger than 1 over k. Right, because as I'm taking square roots, yeah, that should work, right? So the square 1 over root 10 is greater than 1 over 10. Yeah, that should be fine. And this thing diverges, right? I guess we should say 3 to infinity, but whatever. So by the BCT, diverges like that. Okay, so that's the idea. BCT is nice. Again, though, if it was even like k plus 2 in the denominator, all of a sudden we're in a lot of trouble, right? So in typical fashion, BCT is nice, but it has a lot of limitations, right? No pun intended. So what we need to do is we need to, yeah, no, that was a bad joke. So what we need to do is we need to build up to having, a couple more tools. And in fact, like I said, we're going to have a lot of tools. These are sort of nice in the sense that the examples that I've given you here aren't that different than improper integrals, right? All of these things are functions that I've given you so far. These are just functions that you have, of real numbers. And these are restrictions of those real functions to the natural numbers. So we're kind of used to playing with them. But what happens when I start giving us things that are like sequence specific? You know what I mean? Like things like -1 to the power of n, which is something that doesn't have a really nice sort of analogy as a real function, or n factorial, which again, you could use the gamma function, but you probably don't want to, right? So as we start to get into things that are really just about sequences themselves, do we have tools to deal with those things? And so again, our toolbox is going to be a little bit more sophisticated for series as a result of that. But that's not today, right? That's next week. So first things first, let's now prove the p-test, right? And the p-test statement, pretty simple. It's the exact same, again, as it is for improper integrals. This converges if and only if p is greater than or equal to 1. Okay. And so when we did this for improper integrals, it was no problem, right? You're right. Sorry, strictly greater than 1. Yeah, thank you. So when we did this with improper integrals, it was no problem because we actually could explicitly figure out what the integral of 1 over x to the power of p was. But now we're in a lot more trouble because we have no idea what these are, right? We've seen that even for when p is equal to 2, right? Like 1 over k squared, we get something like pi squared over 6. So this is going to, in some sense, actually be a significantly more complicated proof than we had before. Okay. So first of all, let's prove what happens if P is less than 1, less than or equal to 1, okay? So if P equals 1, it's the harmonic series and we're done, right? This is the harmonic series. So we're done, okay? So now let's assume P is less than 1 and show that it diverges. This is actually the easy direction though. So let's show this diverges. And the answer to that is we're just going to use the basic comparison test, right? And basically we're going to do exactly what I did above. I wanted to show that 1 over, the square root of k diverged. How did I do that? I said, well, look, hey, it's bigger than 1 over k. And yeah, that's going to be true here as well, right? So if p is less than 1, note that 1 over k to the power of p is going to be bigger than 1 over k, right? Because p is less than 1. So if p is between 0, like this is kind of silly. You don't even have to do anything if p is negative, right? If p is negative, you're done because the sequence doesn't, like the terms of the series don't even go to 0, right? So if p is less than 0, you're not worried about it. If p is between 0 and 1, well, 1 over the pth root of k is less than equal to, is less than k. So when you reciprocate, you're going to flip that inequality sign, right? And now by the basic comparison test, the harmonic series diverges. So therefore, so too does 1 over k to the p. Diverges. So 1 over k to the p diverges. Okay. All right. So now the actual tough part of this is to get into the meat and potatoes of this, which is what happens when p is greater than 1. So if p is greater than 1, what do we do? So it'd be nice to have something to compare this against. And it turns out, in fact, it's not too hard to show that 1 over k squared converges. And the moment you get 1 over k squared converges, you get everything for p greater than or equal to 2, right? So if 1 over k squared converges, basic comparison now gives you 1 over k cubed, 1 over k to the 4, 1 over k to the power of pi, all of that stuff. But of course, our problem here is that we don't have sort of like a smallest number, a smallest real number closest to 1, right? So that's great. We could do it for a fixed point and then, say, oh, for all the p's bigger than that, we converge. Unfortunately, we have to do something a bit more complicated. All right, so yeah, let's monotone convergence theorem this thing. Okay, so if p is less than 1, since 1 over k to the p is greater than 0 for all k, the partial sums, let's give them a name. The partial sums Sn are strictly increasing, actually, right? So this is, again, one of those things. Our summons, right, the things that we're adding together are all strictly positive. So that must mean, therefore, that our sum is actually strictly increasing. Great. So all we need to do then is show that it's bounded from above in order to prove that it converges, right? So let's show that it's bounded from above. Okay, and this part's a little bit weird. So what we're going to do is we're going to look at the odd terms. And this is sort of a typical thing that we do when we're dealing with sequences. So you might want to look at or especially with partial sums, you might want to look at a subsequence, just because, even though we can't necessarily conclude convergence by a subsequence, if we want to be able to like group terms together, often we have to look at subsequences. So again, I've got something on your next assignment that's going to sort of coach you through how you can do this. So let's look at the odd subsequences. So let's look at the odd subsequences or subsequence. Okay, I need to give it a name. What do we call it? S to the 2. I guess n, 2 to the n. Not 2 to the power of n, 2 to the n plus 1. Okay, so what is this going to look like? So this is going to look like, is there a nice way of me doing this? Well, here, let me just write it out in pieces. So 1 to 2n plus 1, 1 over k to the p. Okay, so I'm going to pull out the k equals 1 term. And then I'm going to do a dirty little trick here, which is I'm basically going to, the reason why I want the odd term is because I want to be able to group together adjacent things. So I'm going to rewrite this now as the sum from k equals 1 to, or sorry, not 2. Yeah, no, still 2. Sorry, this should be 2. So k equals 1 to n. I'm going to double check these numbers in a second. Just give me a second here. 1 over 2 to the 2k to the p, 1 over 2k plus 1 to the p, right? So let me double check. So I start with 1 over 2 and 1 over 3. And if I plug k into this, I get 1 over 2, 1 over 3. So that looks right. And then I finish at 2n and 2n plus 1 to the power of p. Yeah, that looks right to me. Does that look good? Does everyone see those are the same? You might have to stare at it for a second, but stare at it for a second, convince yourself that those are equal. Okay. So now what I'm going to do is I'm going to bound everything in that bracket. Remember when we were talking about the harmonic series? And I grouped them into powers of 2 and I bounded everything by the lowest number in each group. So I'm going to do the same thing here. So I'm going to bound everything by the lowest number in its group. Or actually, I guess the biggest number in its group. What do I want to bound by? So I want to bound by this, and this is less than that, right? So if I replace 2k plus 1 with 1 over 2 to the k, that's going to be hopefully less than. Let's see. Let me just write it out and then we'll see. 1 to the n. I hate inequalities. I don't know if I've ever told any of you that. Okay, is that true? Yes. Yeah, right, because 2k plus 1 is less than 2k, and p is bigger than 1. What, did I hate inequalities? The no way? I can't tell if that's sarcasm or like, I totally, like, you knew that because I've expressed this hatred on multiple times. Everyone should hate inequalities, as far as I'm concerned. I have friends who like, okay, sure. Yeah, I have friends who, do you guys, now I guess you guys probably don't know Parker, but Parker's entire PhD involved with like doing homological bounding arguments. So his entire PhD was like doing inequalities. And I was just like, I don't know how you can do that. Yeah, you're a crazy dude. Crazy dude. That's the thing though, right? Like if you go and you take analysis, there are a non-trivial number of those analysts whose job are just to like bound things, right? Like that's their job, is just to find bounds for numbers or sequences or functions or whatever the case might be. So 2 over 2. So I'm doing a lot of steps here because I am just not, if I don't do a lot of steps, I'm going to screw up. So p minus 1. And now this is S n, right? Yes. Okay. So what does that give us? So I guess what I'm going to do now is I am going to cheat and say, well, Sn is less than Sn2n, S2n plus 1. And I know that this is an increasing sequence. So this thing is here is strictly less than 1 over 1 plus 2 to the p minus 1, s to the 2n plus 1. Okay, is that okay? Again, and this is part of why I hate sequences, or I hate inequalities. I like sequences. I hate inequalities. Because I got it down to Sn, and I'm like, okay, well, I actually need s to the 2n plus 1 there, so I'm just going to stick it in. And I can do that because, again, I know that the sequence is strictly increasing, right? All right, great. So what am I going to do now? So now I can rearrange this equation. So I'm going to get s. What am I going to get here? So I'm going to get s to the 2n plus 1 times 1 minus, maybe let's just write this as 2 to the 1 minus p or something. So that's going to be less than 1. So s to the 2n plus 1 is less than 1 over 1 minus 2 to the 1 minus p, right? And that does not depend on n. So that is actually an upper bound now for my sequences, which is an upper bound. Okay, so that upper bounds the odd sequence, but of course the even sequence is therefore bounded as well. For the odd subsequence, this is a bound for all Sn, since, well, again, we know that S2n is less than S2n plus 1, which is less than 1 over 1, 2 to the 1 minus p, right? And yeah, every element of the sequence either has an even or an odd index. So now I've shown that every single element of the sequence is actually bounded from above. So now I have a strictly increasing sequence, which is bounded from above. So it converges by the monotone convergence theorem. Thus, by VMCT, converges. Right? And yeah, so there's sort of like the proof here. Let me zoom out. There's the proof for p greater than 1. That's way worse than what we had for the improper integral, right? Like significantly worse. Because with the, like I said, with the improper integral, we actually could just integrate that function. And then we could just, hey, does this thing converge as x goes to infinity? The answer was yes, right? Here, we had to do a lot more magic and a lot more inequality mess. And it is what it is, right? Like, what are you going to do? So we're really leveraging here, right? There are a couple of things to really note. What did we leverage? So we leveraged the fact that the partial sums were strictly increasing. That was really, really helpful because it allowed me to say, well, okay, if I know something about the odd subsequence, I can then sort of extrapolate that and say something about the even subsequence as well, right? So the fact that I knew that the partial sums were strictly increasing was really beneficial. And that came because the summons were non-negative, right? So that was really useful. And the other thing is that unlike most sequences where two adjacent terms of the sequence generally don't need to be related to each other, right? Like if I give you a sequence AN, A7 and A8 don't really need to be related to one another. In a partial sum, they obviously are, right? And the way that they're related to each other is precisely through that sequence. You know that S8 is S7 plus A8, right? So the fact that the sequence of partial sums has more structure than a generic sequence, right? You can say more things about it, is very, very nice. You have to be careful in your brain, though, to sort of separate it from normal sequences, right? Partial sums have a little bit more structure, and there's a little bit more powerful things that you can do with them versus just normal sequences. And here's an example of something that we can do. Because n is less than 2n plus 1. And the sequence is, yeah, and then the sequence is strictly increasing. Okay, so that's pretty nice. I guess I didn't, no, I did need basic comparison, right, to do the p less than 1. I was like, can I do this before basic comparison test? And the answer is no, unless I want a different proof for p less than 1. But okay, great. So there we go. So the p, yeah, having the p test is nice. And again, remember, this doesn't have to be for like integer p, right? Or even rational p. This is real p, right? We've proven this is true for any real number p. So that's pretty good. What do I want to do? Yeah, let's just go straight to limit, because once we have limit comparison test with p-test, we unlock a lot of things, right? So let's then just go straight into limit comparison, because the examples of this are just going to be basic comparison with p-test, right? They're kind of boring. So theorem. So limit comparison test. All right, so again, the theorem is basically, the motivation for it is the exact same as it was for improper integrals, and the proof is pretty similar as well, which is basically sometimes the basic comparison test doesn't work out just because the inequalities don't work out. But morally speaking, if the inequalities don't work out for a stupid little reason, that shouldn't inhibit your ability to prove convergence. What you just want to say is, hey, can I take my series and can I compare it to something which morally is the same thing, right? Is morally doing the exact same thing as your index shoots off to infinity, and then use the convergence of that thing in order to be able to determine the convergence of your original thing, right? That's sort of the idea. So again, let's set it up. So let's suppose I have two sequences, AN and BN, be positive sequences. Okay, what else do I want? And that the limit of their quotient converges to some positive non-infinite number, right? So it actually converges. The limit as k goes to infinity of AK over BK is equal to L for some 0 less than L less than infinity, right? So it converges, and it converges to a strictly positive thing. So again, morally speaking, this means that AK and BK are basically the same thing, right? In order for this to give you a finite limit as k goes to infinity, they're morally behaving the same way, right? Up to some like multiplicative constant L, okay? In that case, then the series AK converges if and only if the series BK converges. So we're going to do some bad English here, start our sentence with then. Converges if and only if BK converges. Okay. And again, the proof is basically the same way that we did with improper integrals, which if you remember, we take this limit and we can use this limit to basically set up a basic comparison test, right? So the proof looks something like this. So since the limit as k goes to infinity, AK over BK is equal to L, let's set epsilon to be L over 2, which we can do, right? Because L is strictly positive, it has to be. So that means epsilon here is strictly positive. And choose some n such that if n is bigger than n, then what? AK over BK minus L is less than L over 2, right? Because that's our epsilon. And then we do our usual thing where we kind of like expand this out, put L over 2 on each side. So we're going to get L over 2 is less than AK over BK is less than 3L over 2, right? Little n is, oh yeah, you're right, sorry, K. There we go. Right, I told you, right? I'm going to confuse little k and n a ton. Okay, so what does this give us? So because the terms of this sequence are non-negative, are actually positive, strictly positive, then if I multiply, I'm not going to break anything, right? So if I take this expression now and multiply by BK, I'm going to get L over 2 BK is less than AK is less than 3L over 2 BK. Right? BK is positive, doesn't screw up my inequalities. All right, now, if BK converges, great. So so if the sum over BK converges, then we've got AK is less than 3L over 2 BK. And well, the sum of 3L over 2 BK obviously converges as well, right? Because I can just take, let me put my K's in, because I can take the 3L over 2 out. It's just a constant, and that converges. So now what do I have? Well, I have that I've bounded A above by a convergent series, right? So by the basic comparison test, the series in AK converges. So by the BCT, the sum in AK converges, right? And then number 2, so it's an if and only if. So again, we're kind of going to do it by doing like the forward direction and then the contrapositive of the forward direction. So instead of assuming that AK converges, which we totally could, let's assume BK diverges. So if BK diverges, then AK is greater than L over 2 BK, right? So now I'm using the second half of that inequality. And of course, the sum, if I throw the L over 2 in there, that doesn't affect divergence. Right? So by the BCT, the sum diverges. And we're done, right? So it all comes down to this equality or inequality, which basically says, yeah, we can bound AK just, sure, we might need to use some sort of multiple like L over 2, 3L over 2, but basically we can bound AK by BK in both directions. We can bound it above by some multiple of BK and below by some multiple of BK. So there's this little like channel, there's this little pocket of BKs, and AK is forced to live in between it. So if BK diverges, it's going to force AK to diverge. And if BK diverges, what did I say? If BK converges, it forces AK to converge. If BK diverges, it forces AK to diverge. Because again, it's like, they're escorts and AK has to live in between it. And so whatever BK does, AK is going to do as well, right? Like that's not a crazy thing. So there you go. Now we have a limit comparison test. And again, that's why kind of morally speaking, if you look at this theorem statement, this condition is really saying AK and BK are morally doing the same thing, right? Like they're really not that different. Sure, if one might be twice as much or 3 times as much more than the other, but it doesn't matter. That factor of 3 doesn't make a difference as you shoot off to infinity, right? A convergent series and 3 times a convergent series are basically the same thing. Or maybe I should say like if the series converges 3 times that series converges, right? Like that's not crazy. Okay, any questions about that? And I guess I could try and do like a quick example. I mean, the quickest example is to do the one I said we couldn't do before. Right, so determine again, I have to be careful about my index here now. Right? So the first example that we did had 2k plus k, which fine, no problem. The basic comparison test works out well. But the moment I have 2k minus k, suddenly I'm in trouble, right? Because again, the obvious inequality to use here is going to be the opposite of what I need for the basic comparison theorem. So, but with the minus here now and the limit comparison test, no problem, right? So let's say let ak be 1 over 2 to the k minus k, and bk equal 1 over 2 to the k, so that ak over bk is what? So it's going to be 2 to the k all over 2 to the k minus k, right? We need to show that this thing has a finite limit. And you remember that trick I showed you the other day? You can do sort of the same thing. Like I can just see this limit is 1, right? Again, the minus k really isn't doing anything as k goes to infinity. But if you want, what you do is you sort of like multiply here. Maybe let me put this in here. You multiply everything top and bottom by 1 over 2 to the k, right? Or 2 to the negative k if you want. And you get 1 divided by 1 minus k over 2 to the k. And you might have to convince yourself that that thing goes to 0, but it definitely does, right? Like use L'Hopital if you want. And if you L'Hopital k over 2 to the k, you're like, oh yeah, that goes to 0 after one application of L'Hopital, like really, really quickly. And you get 1. Okay, great. So you've shown that these things, ak over bk has a positive finite limit. So that means that they morally behave the same way. And bk converges by geometric series, right? Due to the blah converges since it's a geometric series. Right? Thus, by the limit comparison test, so too does this thing. Right, great, done. So it's a little bit more work because you have to prove this limit, right? You don't just get to write down like the simple inequality and say, hey, I'm done. But whatever. At the end of the day, that's probably way easier than trying to make a basic comparison test argument with this function, because it just, again, it's kind of like fighting you. It doesn't want to do what you want it to do, right? So that's how you're going to handle these things. Okay, any questions about that? Is there anything else I want to do? I mean, everything is basically just a sort of copy of this. No, it's good. It's good. Okay, so yeah, I'm not gonna do another thing there. If you guys really want, like, I'm definitely not going to stop you from looking up basic comparison test and limit comparison test on Google. And if you want like a ton of examples of these things, because this is a fairly standard thing, right? Like in Math 135, 136, and 137 for that matter, students there learn basic comparison test and limit comparison test. They don't learn the proof, right? That's something that, we would do. 137 would do the proof, but the 135 and 6 students aren't going to learn the proofs of these theorems, but they are going to use them. Right? So if you want lots of examples of being able to do this, it is a standard enough problem that it's very easy to find just a plethora of examples to do this. So It shouldn't be too hard. Just, use your Google foo and find a bunch of BCT, LCT. And in fact, this is going to be true of next week as well. So next week, we're going to talk about the alternating series test. So this is what happens if, right, both of these theorems required that your terms were always positive, right, or non-negative. But what happens if they alternate? Like, what if it goes positive, negative, positive, negative, positive, negative? Turns out you can say some really strong things about those series. So we're going to learn the alternating series test. Then we're going to learn the root test and the ratio test. And those three tests as well are like standard, right? Those are standard things that they would learn in 135, 136. And so if you want examples of those as well, easy to find lots of them. Some of the things, so if you want kind of like specifically 257 things, first of all, obviously we're going to prove those, and certainly they won't prove those in 135, 136. I'm trying to think of whether they would in 137. Maybe they would. I can't remember. But yeah, your assignment for sure has a test, has a convergence test that they would not see in either of those classes. And it's not too hard to prove, right? And again, I've kind of scaffolded it for you so you know exactly what to do. But it is a very cool test that you can try out. So, if you want like if you want to see like a 157 thing, go look at your next assignment, and it's sort of got one in there for you. And there are a ton of tests. There are a ton of series convergence tests. Usually we stop after root or ratio, just because after that they start to get really weird and obscure. But if you want to pursue it a little bit more, my book does go into like Rabe's test and Kummer's test and all of these different sorts of things, which actually generalize the tests we're going to learn next week. Okay. And then again, try and prove the integral test. So that's another thing you can do, right? Just prove the integral test. All right, everyone. So I don't have anything else to say there. I think we can call that a day. Have a good weekend. Do well on your assignment, and I'll see you next week. And the marking should hopefully be done pretty quick here. Sophia, sure. Yeah, if you want to hang around a bit. You too, Nicole. See you later. Mm-hmm. Sure. Okay, but so where do you want to use that? So 1 over, I mean, that is true, but 1 over 2 to the k would be less than 1 over k, right? So,
like,
yeah.
Okay, are we going to see the BCT or not? Like, that was my question.
Are we gonna do what with the BCT?
Like, are we going to like see it? Because like to resolve the sum here, 2 to the power of k minus k, you said that we had to do L'Hopital. Like, we just need to use BCT, no?
Oh, I see what you're saying. Maybe not BCT, but like you're saying in the argument here where that thing goes to 0.
Yeah.
So, I mean, basic comparison, usually, remember we use that for series. And at this point, I'm just arguing that the sequence k over 2 to the k goes to 0, right? So in some sense, yes, the fact that 2 to the k is bigger than k is advantageous there. But being just strictly bigger isn't enough because, n is less than 2 to the n, but their quotient doesn't necessarily go to 0. Right? And yeah, I'm not like, there isn't a series here. So it's not basic comparison that we want to use, right? We just want to argue, hey, this goes to 0 as a sequence, right? And if we can prove that the function x over 2 to the x sort of thing, if that goes to 0, so too must the sequence. And then I was just saying like, hey, listen, if you want to do that as a function, right? Then once you L'Hopital it, you get like 1 over 2 to the k ln 2. And now that thing definitely goes to 0.
All right, so we couldn't use BCT because like, yeah, there are contour examples that like don't go to 0. Thank you.
Yeah, okay, sure, yeah. But like I would just say like be hesitant about saying BCT, right? Because basic comparison is for series, right? And here is just a sequence that we're trying to show as zero. We're not trying to add up these terms, right? We're just
Okay.
showing that they go to zero.
Okay.
Mhm.
Thank you.
No problem. Okay, anyone else? Anything else? Everyone's just hanging out. All right, Shu.
I mean, I just have like a very specific question, not
Okay.
about course content, but I cannot like focus for the life of me right now at all on anything with school. And do you have like any advice at all? Because I need to finish the semester. I'm not going to drop like 3 weeks before, exams. But I just like I've tried every practical solution I can. I feel like I'm just missing like life experience or something to be able to like complete my work right now. Yeah, I mean, I guess that's it.
Yeah, I mean, this is tricky. So I mean, usually when traumatic things like this happen, people dropping out is not weird and it's not unusual, right? And that is how some people deal with it. I was sort of like fortunate enough that nothing too traumatic happened when I was in school. So I don't necessarily have great like personal experience in order to be able to say like, here's how I dealt with it. I mean, what I would hope is that, like you kind of mentioned, we're so close to the end here that even if the rest of the semester is a total wash, if you have retained what you've had, what you've got so far, when the finals come up and everything, hopefully you can just do well enough that you can get through it. And I think maybe that's got to be the goal. You could try reaching out to, I mean, it's just because it's COVID. I think the mental health people are kind of overwhelmed right now, but I would try maybe reaching out to them. They might have better coping things, because this is something they for sure would deal with all the time, right? Like, sometimes people's parents pass away while they're in school, and then they just, people can't focus. So the counseling services definitely would, I think, have probably better techniques for this. But I also kind of suspect that they're just slammed and it might be hard to get to them. Have you talked to like the registrar and just seen if like what they've said?
I Well, I've definitely thought of the mental health figure, although I have my own resources, so that's not really my issue. Is very like course specific. What would the registrar like be able to do? Because I mean, my definitely agree with you with I would love to just be able to bank on, what I have so far for courses, but like with 157, I'm not sure if I will pass. Like
Okay, so yeah, here, let's do this. So right now, what I'm kind of aiming for is like a take-home final exam, right? Which we'll hopefully vote on in the next couple of weeks here. That I think, in terms of like all things considered, like if you're having trouble focusing, for sure, that's not necessarily a solution to that, but that might be more doable, just in terms of like a spread out thing,
for sure.
which would hopefully give you like more chances to succeed, I think, right? But yeah, I mean, if we kind of have to throw out the rest of the term just because stuff is going on, that's fine. From like an academic viewpoint, that's okay. There does still obviously need to be some sort of final assessment. But again, if it's a take home, hopefully you find a way of managing to scrounge that up enough. And I think that's like, yeah, what else could we do? It's just kind of hard to.
No. I mean, that's already so much, because I didn't. Well, you're saying, I mean, if we can scrap the rest of the term, well, I might have to ask you again to move the next test, because
yeah. And this is what the registrar can do as well. Like I can, in some sense, just informally do this, but what the registrar can do is formally say like, yes, Sophia basically can get a pass on a lot of the stuff that's coming up, right? Which might be useful for other classes as well. Like I said, in this class is sort of small enough and is, it's a specialist class, so I can basically just do this. But especially if you need this for other classes, it might help. I don't want to say that this is, well, it might actually be something that you want to register with disability for, even if it's just a short-term thing, right? But like the Accessibility Center specifically has things for dealing with this, and the channels there already exist. But the registrar might be able to just give you a note which says, yeah, Sophia, like it's a pass on like upcoming assignments and stuff. You know what I mean? Like that stuff gets relegated.
I had no idea. Yeah.
I mean,
thank
you can
so
ask,
much.
right? Like I'm not 100% certain, but it doesn't hurt to kind of maybe go through that process and see what they say. And, explain to them the circumstance and stuff.
Okay. Yeah, no, thank you. I didn't even think they could do something like that.
Yeah, it does sometimes happen. Like, especially if we have students, for example, with chronic medical illness, sometimes we just get notes saying like, hey, this student has been in the hospital for 6 weeks. Like, what are they going to do? You can't give them zeros for that sort of stuff. So, talk to them and see what they say.
Okay. 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 Thank you so much.
Yeah, no problem.
I really appreciate it. Have a good weekend.
You too. Good luck.
Bye.
Bye. Anyone else? Nicole, Summer, you guys good? I'm going to assume yes. Yeah. Okay, cool. Bye, everyone.